All right, guys, we're still working in section 4.1. It takes us a few days to get through all of section 4.1. Today, we're going to start working with the graphs of a polynomial. So again, I'm pretty sure you're familiar with the graph. There's just a couple new vocab words that you have to get used to hearing, okay? Let me just tell you that today, I normally don't give homework on the second day of section 4.1 because it's a lot of just information and not a lot of doing examples that I kind of get to go over with you. However, I did post the homework, but I probably won't be able to show you all of the types of problems that are on it until after tomorrow, but I posted it just in case anybody wanted to get started on it, because again, I'm pretty sure you're familiar with a lot of this information, okay? But it's not due till Thursday, just to give you guys time to see today and tomorrow's notes to work on it, all right? All right, but yesterday's notes, we were working with the graphs of even and odd power functions and just noticing some differences and some similarities. One of the major things they want you to focus on is the fact that the graph of y equals x squared, x to the fourth, x to the sixth, x to the third, x to the fifth, and x to the seventh, they have this x-intercept at 0. However, it's an x-intercept that gets repeated. X equals 0 2 times, x equals 0 4 times, x equals 0 6 times. We call that the multiplicity of that 0, the multiplicity of that x-intercept, and they want you to notice that the more that x-intercept is repeated as a 0, there is this flattening out effect on the graph as it passes through that x-intercept. And then one of the major differences between even multiplicity and odd multiplicity is when the x-intercept was repeated an even number of times, when the graph hits that x-intercept, it didn't actually cross over the x-axis. It just bounced and went right back in the direction from which it came. So that's an important thing you want to know about even multiplicity, is that the graph is not going to cross over the x-axis at that x-intercept. It's going to touch it or be tangent to that x-axis at that x-intercept, but it doesn't cross over. When the graph has odd multiplicity at that x-intercept, yes, there's that flattening out effect, but it actually still crosses over the x-axis. So that's something that you have to notice that this is going to talk about, because ultimately the goal of section 1 is for you guys to be able to create the graph of a polynomial function as quickly as possible with having to do as little work as possible. All right, so please take that into account. Odd multiplicity, it will cross over at that x-intercept. Even multiplicity, it will not cross the x-axis at that x-intercept, okay? All right, let me start today's notes now. Okay. All right, so just to kind of recap a few things. Polynomial functions are expressions that can be written in this form, right? Where you are in descending order from highest power down to your just number. All right, a power function is basically just each individual term of your polynomial is a power function. It is a form of a sub n times x to the power of n, right? It's just purely multiplication and exponents going on as its operations. All right, they're gonna mention the word power function a lot, so you just want to be familiar with it. So remember, a polynomial is just the sum of many monomials terms or power functions. Okay? All right, the graph of a polynomial function. I hope you guys already remember this from last year. It's the whole, hopefully your teacher was talking about the whole one up, one down, both up, both down, all of that end behavior. That's usually what we depend on to kind of sketch the graph of a polynomial very, very quickly. All right? The graph of a polynomial is a smooth, continuous curve that is always going to have a certain number of x-intercepts or zeros and a certain number of turning points. Guys, the one thing you got to love about a straight line is that one of the first things you're asked to graph is that it just goes in one direction. It never turns and changes and goes back the other way. So the higher the degree of your polynomial, the more chances it has to turn and become increasing, decreasing, increasing, decreasing, all right? More of that roller coaster effect. So the higher the degree, the more turning points your graph could have, all right? Turning points are where the graph changes from increasing to decreasing. These points are also known as the local maxes, right? Those peaks and those valleys that we were looking for before, or minimums of the function. In between each x-intercept, the graph of the polynomial will either be above or below the x-axis, right? Either your graph will be above the x-axis in between x-intercepts, or it'll be below the x-axis in between x-intercepts. At any x-intercept, the graph of a polynomial can do two things. It's either going to cross over the x-axis at that x-intercept, or it'll just touch the x-axis and be tangent to it at that x-intercept. Usually I call my touch the bounce. It kind of bounces off the x-intercept and goes back in the direction from which it came. All right, so again, that's going to have to do with the multiplicity of that x-intercept. We know that odd multiplicity will cross over. We know that even multiplicity will bounce, okay? And that's another clue that we're going to be able to use to create the graph of a polynomial very, very quickly, all right? Okay, let's see. I got to move mine up. Well, I think I can fill this in. So they want you to understand that when we go to graph a polynomial, we have to want to know or see what's going on at the end of the graph. As x gets really, really positive, or as x gets really, really negative, what's going on either end of the graph. So for large values of x, whether it be positive or negative, right? Whether you're heading towards positive infinity or negative infinity, the graph of a polynomial function will resemble the graph of its leading power function. Okay? So do you guys remember when you were in Algebra 2 last year, if you were asked to graph this polynomial function, right? A lot of times you'd have to find out what degree is it, what is the sign of the leading coefficient, and that's how you could kind of predict that whole which end is up and which end is down nonsense. So they're telling you that the graph of a polynomial function, it always resembles the graph of its leading power function. So this graph of this polynomial, the end behavior is going to look just like the graph of 1x cubed. And it's kind of like, well, why is that? Why is the end of the graph just going to look like him? What happens to all of the other terms in this polynomial? Well, guys, you have to think about it. If I was to factor x cubed out, if I took x cubed out of this expression, right? Like divide everything by x cubed. All right. What's going to be taken out? I have 1. Plus, then I'd be left with what? 5 over x squared minus 3 over, I'm sorry, just x. 3 over x squared, and then plus 2 over x to the third. So when you start plugging really, really large values of x in, as x heads to positive or negative infinity, when you start plugging really, really big numbers in, what's 5 divided by a really, really, really big number? Practically 0. What's 3 divided by a really, really, really big number squared? Practically 0. What's 2 divided by a really, really, really big number cubed? Practically 0. So what's 1 plus 0, 0, 0? It's 1. So when you're done at the end of this graph, your graph is acting like x cubed times 1, which is x cubed. So the graph of this polynomial function at its end, when x is huge or really, really negative, it's going to behave like the graph of 1x cubed. So when we're graphing polynomial functions, a lot of the information we need to know about its graph and its end behavior just come from that leading power function. The rest of the polynomial is insignificant to us when we're using really, really large values of x. All right? So therefore, we will use the leading power function to predict the graph's end behavior. So we're going to rely very heavily on that first term. Just give you a second, and I'm going to move it up. Case, do you remember that, like when you were graphing polynomials?
Yeah.
All right, so here we go. So just some quick properties of polynomial functions and what we're going to have to know about their graphs. So guys, here's an example of a linear polynomial, a degree 1 polynomial, right? The highest power on a variable is 1. A's, B's, and C's, those are just going to be replaced with numbers. So guys, I hope you remember that the number of zeros or x-intercepts that a linear equation could have is at most 1. The degree of a polynomial tells you at most how many x-intercepts or zeros that graph can have. All right, the turning points. How many times is a straight line, a degree 1 polynomial, going to turn around and change directions? It doesn't. There's a theorem that says the number of turning points is always 1 less than the degree. Right, we call it n minus 1 if n is the degree. So a degree 1 polynomial is going to have 1 minus 1. It's going to have 0 turning points. And then the end behavior. Guys, a linear is degree 1. That's an odd degree polynomial, so the end behavior is opposite. And again, I hope you remember all this. One end will be up and one end will be down. All right, a degree 2 polynomial. It can have at most 2 x-intercepts. Now, the reason we say at most is technically a degree 2 polynomial will have 2 x-intercepts, except sometimes you get the same x-intercept twice, like x equals 3, x equals 3. It still counts as 2, but you could also just list that as 1, so it may not look like it has 2 x-intercepts, but it really does. It's just a repeated x-intercept. All right, so at most the number of turning points, well, 2 minus 1, a quadratic can turn at most 1 time and change direction from increasing to decreasing. A quadratic is an even degree polynomial, so the end behavior should be the same. Both ends should be up or both ends should be down. All right, an example of a degree 3 polynomial. A degree 3 polynomial can have at most 3 x-intercepts. Again, if you count all the repeated ones, it will have exactly 3 x-intercepts. All right, and then it can have at most 3 minus 1, 2 turning points. A degree 3 polynomial can turn at most 2 times. All right, and then the odd, so it should have opposite end behavior, 1 up and 1 down. All right, and then again, a degree 4 can have at most 4 x-intercepts. And then at most, it can turn 4 minus 1, it can turn at most 3 times. And then the end behavior of an even degree polynomial should be the same, both up and both down. And again, obviously we could keep going, but that's the theme. The number of x-intercepts should be equal to the degree, and the number of turning points can be at most 1 less than the degree. All right? All right, and then the zeros, the x-intercepts of your polynomial functions, just to get, again, some of the wording down. All right? The real zero, not imaginary ones, because they don't actually cross over the x-axis at complex ones. The real zeros of a polynomial function is a value r. So say r is a number that makes this equation equal 0. So if he's a 0, that means he makes the function f of x equal 0. When you plug r into that function, 0 will come out. That's why he's called a 0. Therefore, the following statements are equivalent. Once you know r is a 0, then you can say r is a what of its graph? It's an x-intercept of its graph then. All right? If r is an x-intercept, think about how we find those zeros, those x-intercepts. For example, if we had a factor of x plus 3, we would have set that equal to 0 and got x equals negative 3 as our 0, as our x-intercept. So if you know r is an x-intercept, then you know he must have been a factor of that polynomial at some point. So then we can say x minus r was a factor. Because if I set x minus r equal to 0, I get x equals r. And then we also know that r is a solution to the equation f of x equals 0. I know that r is a number that will make this equation equal 0. I think that's a homework question, all right? Okay, so what we're going to do first, like I said, we don't do too much graphing today. I think we do one and then that's it. When we are leading into getting the graph of a polynomial, the most important points on the graph of a polynomial are its zeros, are its x-intercepts, where the graph changes from positive outputs to negative outputs. So let's just practice finding zeros. So to find a 0, you set the function equal to 0 and solve. If this is a degree 2 polynomial, it can have, at most, 2 zeros, 2 x-intercepts. I'm going to hope it factors so I don't use the quadratic formula. All right, set your factors equal to 0. And you get x equals -3 and x equals 1. So those are your 2 zeros, your 2 x-intercepts to the graph of this polynomial function. All right, let's go over here. Now, when they gift you these ones, you have to be really happy if you set this function equal to 0 and solve. It's
a rule of signs.
What is it? The rule of signs? Yeah.
Remember that one? I couldn't think of that less than.
It's killing you?
I was like, what is that?
So when you set one like this equal to 0, it's kind of like, oh man, they gifted us. It's already factored. But let me just show you something that's going to come into play when we're talking about the multiplicities of a 0, because this is really big on the multiplicities of an x-intercept, how many times that x-intercept gets repeated as an answer. So guys, technically this function, if this is x plus 1 quantity squared, how many factors of x plus 2 does this polynomial actually have? It has 2 factors. So technically you could rewrite this as x plus 1 times x plus 1. There are 2 factors of x plus 1 that live in this polynomial function. Same thing, if this is x minus 3 quantity to the 3rd power, then technically there are 3 factors of x minus 3. So when it comes to recognizing the multiplicity of a 0 or an x-intercept, you have to pay attention to the power that is on that factor. So when you go to solve this, when you set all your factors equal to 0, if I set 5 equal to 0, he doesn't get me an x-intercept or a 0. If I set x plus 1 equal to 0, I get -1. If I set that factor equal to 0, I get -1 again. So -1 is an x-intercept that has multiplicity of 2. It's repeated twice. So that means it has even multiplicity, which we saw on the graph means it'll just touch the x-axis at even multiplicity, but it doesn't actually cross over the x-axis. So they're going to ask you to recognize the x-intercepts where it'll cross over or where it will just touch. When it's repeated an even number of times, that means it's just going to touch the x-intercept or the x-axis at that x-intercept, but not cross over. All right, if I set these factors equal to 0, I get x equals 3, 3, and 3. So that means that's an x-intercept that has a multiplicity of 3. It was repeated 3 times, which is odd multiplicity, which means now we know the graph will cross over at that x-intercept. It won't just touch, it will actually cross over. So again, these are clues that we're going to use to be able to make the graph of a polynomial function come together very, very quickly, okay? All right, let me pause. Everybody okay? Everybody's all right? All right, here we go. Again, other than the word multiplicity, nothing should be new. All right. In example 2, it says, sketch the graph of example 1b using the x-intercepts, the y-intercept, and a sign analysis. So guys, if we're going to graph that, right, a lot of times with polynomials, you're just sketching it. You don't have a point has to be official. So what you would do is give yourself an x and y axis. I don't even label the y-axis because I don't actually find any official y values. They're not important to me. Put your y-intercepts on the your x-intercepts on the graph. -1, -3. So you plot your x-intercepts. I believe in Algebra 2, the way you are asked to graph a polynomial is once you know your x-intercepts, you are then asked to pick a number on each interval, like here, here, and here, and you had to create more points. You had to pick numbers, plug them into the polynomial, and create more. Our job in pre-calc is that you shouldn't have to plug numbers in. You should know the behavior of this graph just by knowing its end behavior and its multiplicities of its x-intercepts. But we're not there yet. So let's just practice. So if you guys did this last year, we're going to use a sign analysis. We ain't going to use actual numbers. We're going to test numbers in each section to figure out where the graph was. Was the graph above or below the x-axis in between each x-intercept? So guys, I'm going to pick -2. You can pick any number to the left of -1. If you plug -2 into this polynomial function, that's going to be a +5. -2 plus 1, I don't care negative because I'll be squaring it, so it'll always be positive. And then -2 minus 3 is negative. Negative to a third power stays negative. So guys, what's a positive times a negative? It's going to be a negative number. That means the graph is below the x-axis to the left of -1. And the beautiful thing is I don't need an official number. I just need to know the sign to know where the graph was laying. All right, if I pick a number in between here, I'm going to go with, let's do 0. 0 is easy. All right, that would be a +5 times 0 plus 1 squared is definitely a positive. And then 0 minus 3 is negative to the third power is still negative. So a positive times a negative is negative. So I know the graph is still below the x-axis in between -1 and 3. And then if I plug a number in over here, I'm going to do 4. So that's going to be +5 times 4 plus 1 squared, positive, times 4 minus 3 is positive to the third, stays positive. That's going to be a positive number. So now I know the graph is above the x-axis to the right of 3. And now, without actually needing any points, I can fill the graph in based off of this information. I know the end behavior is negative, so it's going to be negative. Now, this had a multiplicity of 2, so it's a little repeated. So there should be a little bit of a flattening out effect, and because the multiplicity was even, it should not cross over the x-axis. It should hit it and bounce back in the direction from which it came. Now, if you want to find the y-intercept, go ahead, plug 0 in. I don't care about the y-intercept. I know he's negative. It doesn't matter to me. All right, then I'm going to eventually have to stay in between here, but to get to this x-intercept, my graph is going to have to turn, come back up. This was a multiplicity of 3. So there should be a little bit of a flattening out effect, but it will cross over. And that's what you should be able to do. You should start being able to create these graphs without having to plug numbers in. We did that, but in the future, we're going to use the end behavior and the multiplicities of the x-intercepts to create that graph. And the graphs will come together so fast for these polynomial functions, okay? All right, so let's just fill in our multiplicities, and I may have to stop there because of the time. So again, the main goal is going to be for you guys to create these graphs as quickly as possible. All right, so here we go. The multiplicity of a 0 is the number of times a 0 repeats. The multiplicity of a 0 depends whether the graph of the function will either cross the x-axis or touch it. Again, I call my touch the bounce. Zeros with odd multiplicity, right? When it's repeated an odd number of times. Yes, there will be that flattening out effect. All right, but it does cross over. That's the important part. In odd multiplicity, there will be a cross. The sign of f of x, the y-coordinate, will change on one side of the x-intercept to the other. It will go from a positive output to a negative output. Zeros with even multiplicity. So if they're repeated 2 times or 4 times or 6 times, yes, it still has that flattening out effect, the higher the multiplicity, but the important part is it does not cross the x-axis at an x-intercept with even multiplicity. There's no cross, it's just a touch. So now, if it's just going to touch the x-axis, that means the sign of f of x, the y-coordinate, doesn't change. It was negative, it'll stay negative. It was positive, it'll stay positive on either side of that x-intercepts. All right. All right, I think I can actually fill this part in, and this is stuff that you definitely, I don't think you talk, did you talk about multiplicities in Algebra 2?
Maybe?
Vaguely? Maybe?
Yeah.
I was under the impression every year that multiplicity is the one thing they don't mention to you guys in Algebra 2, but I could always be wrong. All right, but either way, this is the end behavior information you guys should all know, so let's just fill it in and then we're gonna end here. All right, so remember, odd degree polynomials, the end behavior is opposite. One end has to be up and one end has to be down. All right, there's a way to tell which end is up and which end is down. If the leading coefficient to your leading power term, if it's positive, then it's going to be up on the right, the positive side of the graph, and down on the left. So to give you an example of like a straight line, because that's a odd degree polynomial, if it's up on the right, as x goes to infinity, f of x goes to infinity. As x goes to negative infinity, f of x goes to negative infinity. And I'm pretty sure you had to talk like this on that roller coaster of PBA, so you should be familiar with the lingo. All right, if the leading coefficient is negative, then that's when it's going to be up on the left side and down on the right side. Right, so if you think of a negative sloping line, up on the left, down on the right, as x goes to infinity, f of x is going to negative infinity. And then as x goes to negative infinity, f of x is going to infinity. But notice the end behavior is different. One end heads to infinity, the other end heads to negative infinity. Again, do you remember these rules? Do you remember the one up, one down? Perfect. All right, and then the even degree. Remember, even degree polynomials end behavior is the same. Either both up or both down. There's a way to tell just by looking at the polynomial function which end is up and which end is down. If the leading coefficient a is positive, then it's both up. Think about your parabolas. If a is positive, the parabola goes up. So in an upward-facing parabola, as x goes to infinity, f of x goes to infinity. As x goes to negative infinity, f of x goes to infinity. Right, now the end behavior is the same. I'm just going to finish this, guys, and then I'm going to let you guys go. And then the last rule was if the leading coefficient a was negative, then it was both down. So on a parabola that opens down, as x went to infinity, f of x went to negative infinity. As x went to negative infinity, f of x went to negative infinity. So now that end behavior is always the same. Okay? All right, so guys, these are the rules that we're going to use to make graphing a polynomial function come together very quickly and very seamlessly.